Okay, good morning everyone. So before we proceed with this session, can you please clarify if you're MH or MSc? You're MH. Okay. And do you have any projects that you need to carry out?
Group capstone.
Huh?
Group capstone or group dissertation.
Group dissertation.
14. 1 week then. Yeah.
He's only starting to make groups after the late submission is over, late joining.
Yeah, if you need to do any projects with respect to the composites, let me know, okay?
I really hope he does move back to the due date in relation to the fact we haven't been able to fucking start it.
Well, I've had like 2 weeks of not being able to do it.
Yeah.
1 week, 2 weeks.
Okay. So, last session we went through the laminate theory. We didn't finish it fully because there were some tutorials outstanding and some final slides. 2 or 3 slides about temperature effect and moisture effect, which we didn't cover. But let me park that up for now. Go through the laminate theory, not the whole thing, maybe most of, let's say 70% of it, and then I'll go back to the previous lecture. So, before we start, any questions from the previous session? Nothing? Oh, attendance code, sorry. So there you go, this is the attendance code, RXJNYB. And this session is being recorded, just to cover up my back. So make sure what you say is being considered within the perspective of recording of this lecture. And I've tried to upload these on YouTube as well. It's not the best quality videos, but there you go. It will be made available on YouTube as well. Okay, let's begin. What's that? You've got a question with... Sorry, it's a bit noisy. I can't hear you.
This is on temperature and moisture.
I'll get to that. I'll get to temperature moisture.
It's just, we think there's a mistake in the notes. 3 is given in the second row.
I'll rectify it. I'll go through it because, as I explained, I'll go through 70% of the failure criteria, and then I'll go back to the previous session because there are some tutorials outstanding that you need to tackle, and then for the next session we'll deal with the tutorial of this failure criteria. So you've got 1 week to review whatever we've been through, and hopefully we'll give you some ability to tackle the tutorial solutions, if that makes sense. Because I felt that if I asked you to carry out the tutorial on the same day, I could see people struggling. Yeah. So you're gonna scatter it a bit. So do the lecture. The tutorial will be followed in the next week. I think that's a better way of dealing with it. Okay, so today we're going to talk about failure modes and theories of laminated composite fiber reinforced polymers, and have a sort of understanding how different they are with respect to the metallic, aluminium, titanium, steel, generally metallic structures or metallic material. But before we start delving into details of how things are happening with composites, it's quite important to understand the failure mechanisms by which composites fail. What are the predominant failure mechanisms in composite materials? What you see on the screen here is essentially, you can see some fibers, unidirectional, let's say pre-preg, impregnated with resin in a very simplistic, idealistic way. So at the bottom you can see some fibers going, let's call it 90-degree direction. Maybe it's easier if I annotate it on the screen. So you would see some fibers going in 90 degrees, and you would see some fibers going in 0 degrees. And let's assume, for the sake of arguments, this is the loading direction. Or the loading could be biaxial, not necessarily a uniaxial tensile or compression. So one of the means and mechanisms by which composites do fail is through longitudinal fracture of the matrix itself, or the epoxy that puts or keeps fibers together. So if you look at this one here, for instance, longitudinal fracture of the matrix, and if you look at the loading direction, the fiber direction, and the way the crack takes place within the matrix, this is often associated to the fact that shear stress in the matrix reaches the maximum shear strength of the matrix. So you've got shear stress in the matrix as a result of external loading. So this external loading causes some shear stresses here in the matrix. And once these stresses exceed the strength of the matrix, it cracks. And almost certainly for every composite material that you have, this failure criteria is dominant, it's there. So you always have the matrix cracking, longitudinal matrix cracking, whether it's a tensile test you do, shear test you do, whatever you do, this is going to be there. So this is one of the failure mechanisms. Another failure mechanism is that the transverse fracture of the matrix. From this perspective, as you can see here, transverse fracture of the matrix, shown here. Just compare these two, the longitudinal and the transverse and the loading direction. When the tensile stresses in the matrix reach matrix tensile strength, this happens, which is quite obvious. If you've got some tensile stresses in the matrix is not strong enough, it's going to crack and open in the perpendicular direction. So this is perpendicular direction to the loading direction. So the loading is going vertically, the progression of that matrix cracking is horizontal. So let me just get rid of these annotations again. So the loading is going vertically. In this case, transverse matrix cracking is going horizontal, perpendicular to the loading direction, whereas these ones are in the loading direction. In the case of the former, which this one, the root cause is shear or shear stresses, which exceeds the shear strength of matrix. On the other hand, in this particular case, the root cause is the tensile stresses in the matrix that exceed the tensile strength of the matrix. Another failure mode is fiber matrix debonding. So at the interface between the fiber and the matrix, there's a debond. Or when the debonding stress is higher than the shear strength of the matrix, that interface, as shown here, as you can see, fails. Fiber fracture, as you see here, the fiber fractures. The tensile strength of the fiber is not, or the tensile stresses as a result of the loading is higher than the tensile strength of the fiber. Obviously, the fiber fractures. Delamination. So when the interface, so if you look at this as a ply, ply number 1, and then you see this as ply number 2. When the interlaminar shear stresses exceed the shear strength of the matrix again, you will see delamination at the interface here. That's the interface. And the root cause of this, as I said, interlaminar shear stresses. So you get shear stresses at the interface here, shear stresses here. And the shear stresses basically shear out the interface between the plies, and we essentially call them, from technical standpoint, we call it delamination. So as you can see already, we can see the differences between composites and metallics. The metallics just break. There's not. You've got grains in metallics, but not such a thing called as fibers or delamination or matrix cracking. So essentially, the grains inside the metallic material, aluminium, whatever they are, they just break. Okay, whereas when it comes to composite, you've got a lot more complicated damage mechanism that you need to consider. And the question here is how to formulate all of this. When it comes to metallics, we'll get to that in a minute, but when it comes to metallic, you say, okay, von Mises stresses, you've heard it, I guess. Von Mises stresses are this much, compared with the strength of the material, fails or it doesn't fail. Simple as that, easy. But when it comes to composites, how do you formulate longitudinal matrix cracking, transverse one, fiber damage, delamination? How do we do that? Because we need to know that to predict how the material behaves so that we can design something that doesn't fail. That's the challenge with composites, and that's why it becomes quite complicated with composites. Let's see some examples. If you look at the top right-hand corner, it's just showing the stacking sequence for half the laminate is shown. So essentially it's a symmetric laminate, which means you get the exact mirror image of the top at the bottom here as well. So 0, 90, 0, 90 is a cross ply. So the fracture mechanisms that we discussed really depends on three parameters. One is the nature of the constituents. What kind of fiber we're using? Is it glass? Is it fiber? Is it carbon? Is it bamboo? Makes a difference. The architecture of a layer, is it unidirectional as we see here, or is it woven bidirectional, or is it woven through the thickness, or weaved as we call it, three-dimensional weave composite? That's a different story. And then the mode of mechanical loading. Often we see in the literature is tensile testing. Even in industry, what they do is just tensile testing. Nothing else, or compressive testing, nothing else. You don't see any association to combined loading. In real structures, you see, if you look at a tiny element of this structure, let's say here, you would have compressive forces or compressive stresses, and then you would have shear ones. You could potentially have a biaxial tensile here as well. So you can see you can have a combination of forces and stresses on the structure, but we just purely focus on tensile, and that's the case for both academic world and industrial world. But we look at the loads separately and try to come up with an interaction formula to somehow relate these together. So in this particular case, in this example, have a look at the cross-ply. So under a tensile loading, the longitudinal fracture of the matrix takes place, as we explained. So the matrix itself, as I said, is a longitudinal crack like that. You could potentially see it here, but it doesn't show it much. Longitudinal. Fracture of the fibers at the layer of 0 degrees, the load bearing. So these load bearing plies on the tensile loading, these fibers could fracture, as we explained in the previous slides. And also the transverse fracture of matrix in the layers at 0 degrees. So if you remember, that's the transverse. So in a cross-ply laminate, on the tensile loading, you often see these 3 failure modes. If I go back again, roughly how many failure loads do we have here? Can you count? 1, 2, 3, 4, 5. So it doesn't mean you get the 5 failure mode necessarily in everything. In this particular case, you had a cross-ply, the stacking sequence is 0, 90, 0, 90, 0, 90, as we discussed last week about what the cross-ply is. You get 3 failure modes in general. So it just goes to show the dependence of the failure modes on the stacking sequence. So if we look at another example, for instance, this is yet again showing the half the laminate. You've got 45, minus 45, 45, minus 45. Then it repeats underneath as well. So you've got a mirror image of that about the midplane. So if this is the midplane, you would get the mirror image of that at the bottom. So what do we call this kind of stacking sequence? Do you remember that? Is it cross-ply? Is it coarse-isotropic? Angle-ply. So in this case, angle plies, which are really good for reducing stress concentration factors, the angle plies. These 45-degree plies are really good to reduce, 1, delamination, 2, stress concentration. That's why we use them quite a lot. Not in the form of angle ply, in the form of isotropic stacking sequence. So the first failure mode that we often see with these kind of stacking sequences is that the longitudinal matrix fracture in the 45-degree ply, as you see here. We do get delamination between layers of 45s. So how many? How many? How many failure modes? Usually 2 out of 5. So as you can see, in the previous case, we just had 3. In this case, we have 2. It's really dependent. What's the loading? What's the stacking sequence? And therefore, your failure mechanism would be decided or determined based on experimental observations of these, and differs. But generally within these 5 failure modes. Another example. This example is showing, so we looked at a cross ply example, we looked at an angle ply example, and what is this ply stacking sequence? What's it called? What's it called? Do you remember that? I will not proceed if you don't tell me. Quasi-isotropic. Or essentially, quasi-isotropic, just to remind you. So if this is direction X, this is direction Y, the mechanical material property in X direction, for instance, EX, is equal to EY. That's why it's a quasi-isotropic. It's not an isotropic material, it acts like an isotropic material, but it's not an isotropic material. For example, if you wanted to find modulus of elasticity in that direction, it's not going to be the same as, let's say, modulus of elasticity at 45 direction. That doesn't hold valid. That's not valid. Whereas in isotropic material, it is valid. Okay? It's a coarser one. It's not exactly isotropic. So in this particular case, you see a flat panel with a circular cutout here under tensile loading. Tensile loading. What we often see when we apply the tensile loading, one of the failure modes that we see is longitudinal cracking of the matrix in the 19-degree plies, or this one. It is shown schematically. That's the loading direction. Perpendicular to the loading direction, we'll see some matrix cracking. We also see at the 45-degree plies some cracks, as you see here. So it starts with 90-degree plies, because 90-degree plies are not strong. So if you've got fiber going in that direction, let's say if you've got fibers going in that direction, they're not able to carry any load. For structural analysis, we assume this kind of loading is almost zero. You can't take any load in this perpendicular direction. It is there to account for potential loading in that direction, which could happen when you're manufacturing composites, when you're assembling it. It is possible that by a technician, for example, when trying to assemble the whole thing, you could apply loading in that direction. It could happen. So you need to account for it. Otherwise, even before going to on the structure, you have a failed composite or fractured composite. You don't want that. And also, bearing in mind these kind of stacking sequences, I'm probably not going to tell you, or maybe I will tell you later. There are some rules about stacking, particularly for aerospace. How much of each ply you need to use. For example, one of the rules is a 10% rule. You must have, even if the loading doesn't require that, you must have minimum of 10% of the plies in all directions. 10% in 90 degrees, 10% in 45 degrees. Also, you might have a rule that you cannot stack plies of the same orientation more than 3 times, because that causes delamination. So you can have 0, 0, 0, and then you have to change it to 45, 45, 45. You can't have 0, 0, 0, 0, because that would cause delamination.
You know how you said about the 10% rule?
Yep.
If you have like a 60-degree angle, like 15, etc., does that also apply, or is it literally just 90, 45?
0, 90, 45 in real practices. But again, when you step into the world of academia, none of this applies. You know, there is no limit. Sky is your limit. You do whatever you want to do. But industrially, there are these rules. And very rarely, in fact, I have not seen in industry any angle apart from 0, 45, 90. But I've done a lot of research with 15, 30. So these are, again, it's lack of knowledge. Composites it's not new. It's been around since 1980s. But industry is way, way behind or doesn't have the confidence to, or maybe mostly due to the lack of knowledge or not enough knowledge with respect to how to predict the failure if the angle becomes 5, 15. It's generally that too. So, and then the next stage is initiation of longitudinal matrix cracking, initiated from the hole. So if you look at the hole, that's where the stress concentration point is, right at the edge of the hole. That's the stress concentration point. Stresses are high, crack forms, and then you will have some longitudinal cracks going all the way for the matrix. And then these cracks sort of get combined, create secondary cracks, and at the end of the day, your whole laminate fails. So, yet again, this is a quasi-isotropic one. We've had 3 different failure mechanisms, and the loading and the configuration of the structure also determines. So in this case, we have a flat panel with a circular cutout with a structural feature, which is stress discontinuity because of the or stress concentration because of the cutout, and then that determines in what mode it fails. Let's have a look at this one. So, in terms of the failure mode for unidirectional composite subjected to longitudinal tension, so you've got a composite panel, tensile force at both ends. Let me give you 1 minute, digest what you see on the screen, and then we'll delve into it. What do you think is happening? Go ahead, sorry. Yes, you had a question. What's that? Yeah, what's happening here? Do you understand what's going on? Can you make some conclusions based on what you see? You're masters now, so you should be. He was first, so. And then we'll come back in. Yeah.
Is it showing the Young's modulus of the fibre, the matrix, and then the composite of them two together to show how it's stronger?
Yeah. But not the Young's modulus. Strength. Sigma is strength. Oh. But then again, it's not complete yet. 50% there.
I was just going to say that the matrix on the left-hand side one is more ductile than
there you go. Very good observation. Right. Yeah, that's right. Very good observation. So, on the left-hand side, you're seeing here 2 composite systems. On the left-hand side, the same fibers. You'll see an epoxy or a matrix that has got failure strain higher than the failure strain of the fiber. So this is the matrix, and this is the fiber. The fiber on its own. So we're not talking about the fiber in the composite system, just the fibers on its own. Let's say just carbon fibers. And this is the matrix. We know about the rule of mixture, that if you want to find or predict, approximate, again, these are analytical, approximate. It's not what you see in real life. and I'll tell you why later on. It would be what you often find out in real life. The values would be less than what you calculate. So sigma Cu is the strength of the composite, ultimate strength of the composite, when it fails, basically, which is shown here. That's the ultimate strength, which is comprised of the strength of the fiber times the volume fraction of the fiber. Generally speaking, in composites, you're talking about 50%, 60% volume fraction. So in the volume of composites, 50% of that is fiber, and 50%, the other 50% is the matrix. But for high-performing composites, generally it's 60-40. So 60% of the volume of a composite is fibers, carbon fibers, and the other 40% is the matrix. So if you've got the volume fraction, which is, let's say, 60%, times the strength of the fibers, add to that the strength of the matrix, you're talking about the ultimate strength, bear that in mind, times the remaining volume fraction, which is the volume fraction of the matrix, essentially. So that should give you a rough estimate, if you don't have any values from the literature or from your company. There is a way that you can calculate or approximate the strength of the composite. But bear in mind, in this particular case, the strain of the fiber is less than the strain of the matrix. So you've got a matrix which is quite ductile. So it allows the fibers to fulfill its full potential before the matrix cracks. You don't want a composite by which the fibers cannot behave or make use of their full capacity. If the matrix cracks before the fibers fail, then the fibers can't do what they're supposed to do. They can't bind everything together. They can't transfer stresses. So this is actually the ideal composite that we're looking for. But you get in some cases, you will get where the failure. If you look at this one here, the failure of the composite fiber or the carbon fiber or glass fiber is higher than the strain of the matrix, which means matrix cracks first, and then the fiber. So the fiber can't really reach here. So the matrix does not allow us to benefit from the fiber reinforcement, as I explained. These figures might be helpful for carbon fibers. If we're talking about high strength carbon fibers, generally the modulus of elasticity is around 220 gigapascal. But for high modulus, you're talking about 400 gigapascal. That's quite a lot. The strength, you're talking about 3,000 to 4,000 megapascal for high strength. As its name suggests, it's got high strength, so 3,000, 4,000 versus 2,200. And then you've got failure, strain at failure, 1.4% and 0.4 or 5%. So as you can see, high modulus or stiff composites or carbon fibers, they've got low strain to failure, whereas high strength carbon, they've got better strain to failure. That's something to bear in mind. This does not necessarily give you the stiffness that you require, but it will give you ultimate failure strength. Let me give you an example. If you have a heavy structure, you don't want it to buckle. In many of the aircraft aerostructures, not on the spar. On the spar, we do allow buckling and post-buckling, but on the skin of a wing, we don't allow any buckling, because if that buckles, your aerodynamic surface would be compromised. You don't allow any buckling. So for buckling, you want a very stiff structure that resists buckling. But if you've got post-buckling, so you allow the structure to go beyond the buckling region, then you want something that's strong, that can go on and on and on. So it's really dependent on the application. Yeah. Let's have a look at the e-glass. What was e-glass, by the way? Do you remember that? Electronic glass, yeah. So it's good for electrical insulation. And we had another one which was called what glass? Remember that? S-glass, structural glass, yeah. Which is, we use it, they use it, not I, for wind turbine applications. So 70 gigapascal is the, you can also compare 70 versus 400 and 220. So the difference between e-glass and carbon, you can see, is quite significant. Strength, and also strain to failure. One thing I want you to bear in mind from now on, that glass generally has got a better strain, is more ductile than carbon. So one of the problems that we have with carbon is very brittle. When it breaks, it's a big bang, and it just fibers. It doesn't give you any notice. For instance, in aluminium, when you try to break it, you sort of pull it apart. You'll see the narrowing down of the section, necking phenomenon. You can see what's happening. So it'll give you a warning sign. Or in other words, its energy absorption is good. When it comes to carbon or CFRP, you don't see anything. All you know is just bang, gone, finish. You might hear some matrix cracking right at the end of the test, but it's too late. So one of the things that, again, scientists do is to increase the ductility of carbon. They hybridize it with glass. Maybe at the end of this lecture, I will show you one example that we published as well. So we applied glass plies on the carbon plies just to increase failure to strain, to strain to failure. We'll show that in a minute, but just bear that in mind. So, going on the topic of failure modes, unidirectional composites subjected to longitudinal tension for high fiber matrix bonding. So if the bond is good, generally there are two ways of, there are more than two ways, but the common methods of manufacturing composites is, one, for high performing composite, you use autoclave, just to make sure there's enough pressure on the composite, just pressurizes everything together so that the bond is perfect, or so-called perfect. Often that's the case for renewables and aerospace industry. And the other way that we do in UV is hot pressing. So we've got a hot press, we just press it down at a certain temperature, 100 psi, just make sure everything. But with hot pressing, you can't create complex shape, you just flat shapes. You can't really create anything else. But with autoclave, you can use very complex concave shapes. So if the bonding is good, let's say using autoclave, you've manufactured your composite using autoclave, the failure modes are often associated with, so you've got tensile loading, and you often get cracks. In this particular case, failure of the matrix, failure of the fibers, and the failure of the matrix. You get both of them combined, and the crack tries to propagate, let's say to the right, and the brittle fracture happens. There is no debond between the fiber and matrix because the bond is good. We use autoclaving. We use a lot of pressure to make sure the bond is perfect. And it is also possible that you might get these fracture phenomena at different planes, at this plane, for example, and at this plane, or you could get it at that plane. And these planes get joined up. We call it bridging effect. So these are the three phenomena. So let's start with that. The fracture of fibers and the matrix, crack forms, propagates, very brittle, one plane. You could also have one plane there, gets connected through the matrix, as you see here. So that comes up to here, and it propagates through the matrix here. So it comes up to here, fractures this fiber, fractures that fiber, and from that point to that point, they get connected. They call it bridging. When you've got cracks at two different planes, and they just join up. And that's the case for high, or the fracture phenomenon for high fiber matrix bonding. Let's say if your manufacturing process is not good enough, or you've got some flaws and defects during the manufacturing process, that debonding is not being executed, or that bonding procedure is not being executed correctly or sufficiently. You might get a different failure mechanism. I'll ask you. 30 seconds, spend time. I want some of you to explain to me what's happening here.
It's doing the transverse function. Big
What's doing transverse function? I think what it is the matrix is trapped says it's not connected.
Okay. Are you looking at me all the time? I've got it. What's your name? Sorry. Lee. Liam, what's happening here? What do you think is happening?
matrix is fracturing first.
Okay.
Like, falls on a lot how the fibre is trapped in the middle of the matrix.
Okay. Is that it?
No, not that one. Debonding.
Where is that happening? Debonding.
I feel like it's happened all the way along, and then specifically that one. So I feel like it's happened all the way along.
So you haven't applied enough pressure.
Yeah.
Let's say your autoclave was messed up, or generally it doesn't happen with autoclave. Autoclave is pretty damn good. Hot pressing is not, if it's flat plates, hot pressing is good too. So let's say wet layup. So you've got a roller, and you try to apply the epoxy that way. That's not a good manufacturing process. Unfortunately, I've seen it being used on boats. Yeah, these fiberglass boats, I've seen they use it. So it's got flaws, and the bonding could be on the questionable. Yeah, go.
Debonding is the main mechanism of failure, even on like the first one, and then after that the fibers break away randomly.
Debonding is one of them, but it doesn't happen in isolation.
No, but I mean that then causes the other ones. That's why all the fibers are breaking randomly.
To be perfectly honest, the main, if from my experience of doing all these tests, the first thing that happens is the matrix cracking.
Yeah, no, sorry, I'm just asking why it's so uneven where the fibers break. And that's what
Let's see. So what's that? Can you read it? So when you've got a crack, I think something that you should bear in mind. I don't know if you've done linear fracture mechanics. Have you done it or not? Have you been through linear fracture mechanics module? Or you did? That's not good, is it? I think that should be included as one of your modules, really. I mean, so at the crack tip, you've got high stress concentrations. Always know that the notches, the sharp corners in the structure, the stress discontinuity, you've got stress raises, high stress concentrations. So, which means if you have stress of sigma here, you would potentially have stress of 3 to 4 sigmas there. So these high stress, the local high stresses, initiate cracks. So the cracks form. That's the first step. The crack propagates transversely to the fibers without fracture of fibers. Okay. So, as you can see, let's say it goes. So it carries on onto the, oh my gosh, it carries onto the next or neighboring fiber here. Because that crack is in the let's say in the middle of the matrix. The matrix can't take all those elevated stresses. The crack grows onto the next fiber. So when the crack grows here, the debonding happens because you've got high stresses again. The debonding between the matrix and the fiber. So it all starts with matrix cracking as a result of stress concentration. Then the crack grows, hits the next fiber. Elevated stresses at the interface of the fiber and the matrix causes the debonding of the matrix and the fiber. So that means the stresses or external stresses cannot be transferred to the fibers efficiently anymore. It can't do that. So you're losing that surface. You see that debond surface? You're losing that surface. That surface is gone. The stress cannot be transferred via the matrix to the fiber. It can't do that anymore at that particular region. So what does it have to do? it needs to redistribute the stresses. So instead of using that surface, it's got to use that surface here, that interface. Okay? So you have some stresses that used to go through this surface. They don't have any other surface. They have to redistribute, go through this surface and this surface. So these stresses go even higher at these surfaces. So the higher stresses also translate into further debonding. And in the midst of the whole thing, so the debonding is happening, then you get the fibers reaching, as the load increases, the fibers reaching their limit and the fibers fail as well. So as you can see, the common denominator in most of these failures is the matrix cracking, is the root cause of all of that. So that's why I said having a matrix which has got a failure strain much higher than that of the fiber is advantageous. But if your manufacturing process is messed up, you can't still achieve the perfect composite that you intended. So if you compare this with the previous slide, you can see it's very straightforward. Perfect bond, no debonding, matrix cracking happens in this one as well. But the fibers, that's how a composite should behave. That's how we intend it to happen. This is how we don't want it to happen. Okay? That's how not to do it, basically. So manufacturing process is very important.
Do you ever get like a mixture between the two failures? So like
No,
some layers have poor bonding.
Yes. I mean, it does happen. For example, when we try to if you don't have a clean room, when you're prepping your composite, if you don't have a clean room, the dust might settle on one of the plies. That impedes the perfect bonding in that particular interface. And then the remaining of the plies might not have a dust or anything, even a tiny eyebrow hair, for example. So that's why when you do sort of high performance manufacturing of composites, you've got the hat, you've got everything, as if you're a surgeon. Exactly. So it happens in the clean room, and the technicians would be wearing all of that, and then potentially they use robots to cut the plies. So the composites are very sensitive, particularly for again aerospace and space shuttles and space applications. They're very, very. The moment you've got a tiny bit of dust in it, it causes delamination. So you might end up having delamination even before being installed on the structure. You don't want any of that. That's why I hope you can YouTube it, and we can do it later at the end of this lecture. I'm sure you'll find. Just type in clean room composites robots and see what you come up with. I'm sure there are some videos associated to that. But yeah, it's essentially like a surgery, trying to do it with ultimate precision. Even laying these plies, theoretically we say 0, 90, 45. What a nice job. But how can you achieve that 0, perfect 45, perfect, 90? Can you achieve that? So I'd like to show it to you. I'll fire up one of those papers. There are some, we've done it with robotic labs. There are some machine vision techniques that we look at the composite to see how aligned they are. Are they really 45? Because it's possible you might get 43, not 45. You didn't account for any of that. Of course, we use a big safety factor when we design things, but just to account for these unknowns, which doesn't exist when you deal with metallics. Okay, any questions so far? What time is it? 45, okay. So, for poor fiber matrix bonding, as we said, so this was a detailed form of that. So the fracture surface could be like that, a brittle one, depending on how debonding is sort of happening. You could have a bridging effect of different crack surfaces, and you can have multiple bridging. That could happen. Whereas in a perfect bond, this is what you get. So this is one of the ways that you can, when you do go to the lab or when you see this fracture surface of your tensile specimen, you just have a look at it. Does it break like this? Does it fracture like this? Or you would have step one. So because that would be indicative of maybe your manufacturing process was a bit faulty. So these are things to bear in mind. So all of that we explained was the fracture when the load is applied to the direction of the fiber. So if you had your fibers, let's say this is your composite plate. If you had your fibers running in the direction of the loading, these are the fibers, and this is the loading direction. What if the load is applied that way, transverse to the direction of the fibers, or the fibers are aligned 90 degrees to the loading direction? What's going to happen?
It's going to be on the matrix strength.
There's no fiber to take the load, is it? So if it's a perfect bond, the debonding is not an issue, then the matrix is going to crack. If the bond is not good, or maybe in that form, on top of that matrix cracking, you could get the debonding at the interface of the fibers and the matrix. So when it comes to analytical solutions and designing something, we often ignore that kind of strength. If I remember correctly, I can't remember actually. So the strength in the perpendicular direction is around, I think 9,000. Not. I'll tell you in a minute. Let me remember it. It's not zero, but you might as well assume it to be zero. But I've got a figure somewhere. My brain is not working at the moment, so. I put this slide because I thought it's quite crucial to have a comparison, because I need to go into the failure criteria, so you need to know exactly what's happening. So far, level 1, level 2, level 3, dealing with aluminium still all the time. And all you know is how aluminium breaks, how steel breaks, what's the stress strain curve, and all of that. So I'm hoping you remember that the stress strain curve for, let's say, aluminium is similar to that. We call it ductile. And what does ductility mean? Yeah, so you've got high strains at failure. If I told you, what's the surface area under this curve? What's the area under this curve? The energy absorbed. So the higher the surface, the higher the energy absorption of the material. In the case of metallic materials, you see, it's a lot of energy absorption, which is good. That's what you like. But when it comes to composites, it's brittle, which means it just linearly goes up and breaks. Bang, gone. And the surface area, if you look at that, so composites are not that good when compared to metallics, is it? It's not just about strength and light, being light, right? Its energy absorption is crap, let's put it this way. So one of the research that has been carried out at Bristol University was try to use very narrow fibers to mimic or obtain this behavior using composites, and it's been successful. I don't know what's wrong with me today, but the name of the research, I think it's done by Professor Wisnam. He's quite famous in the field. Go ahead.
What happens if you put like aluminium as part of the reinforcement?
With
or
what?
Ceramics.
With
Do
what?
you get more of a ductile curve?
No, aluminium with what? You're talking in the form of a composite. So the composite has got a matrix and a fiber. So you're saying aluminium as a matrix, I would assume.
Yeah.
What's the reinforcement? What reinforcement?
Or I don't know, just an example of like if you put metal into a composite, would you get a more
We don't put. It's not a good idea to put CFRP, for example. I mean, one of the key issues that you need to bear in mind is the thermal effects. The thermal coefficient of aluminium. There's a figure for it, but for composites it's almost zero. So, I'll get back to you. So when it heats up, it elongates, not exactly zero, but it's very marginal, very small compared to aluminium. So when you've got these differential temperatures, it will create stresses and debonding. One of the problems that we had with A380 ribs, what happens, is that for A380 ribs, the ribs, the top portion is is aluminium, the actual rib itself is composite. And because the operating temperature of an aircraft is, let's say, it's minus 20 degrees sometimes. Some people, I think, minus 50 to 85 degrees Celsius. They've created, at the interface of them, they've created slotted holes so that when one expands, the other one, there's a space allowed for that expansion so that residual stresses do not take place. Lots of consider, but you're right. We call it metallic matrix composites. And that's exactly what we discussed, I think, in lecture 1. So it is possible, it's well possible for space programs. Yeah, go ahead.
For something like bulletproof armor, like when they use Kevlar composite, wouldn't you want something like high energy absorption?
Yeah.
When you said that it's not too good at, not too composites aren't that good at.
CFRP is not good at, no. Glass fibers are better than carbon fibers. Carbon fibers have got high strength and high stiffness. That's what you get out of it. So in the applications, you've got buckling, perfect. Aerostructures, perfect. But in order to compensate for the deficiencies, you add another material. It is possible to have 1 or 2 layers of Kevlar to compensate for the lack of energy absorption or ductility in composite, in CFRP. So often that's the case that we amalgamate carbon fiber, CFRP, with GFRP and Kevlar, particularly for impact resistance. Many of these UAVs, not many of them, some of them, at least I know about the Turkish one, what's it called, Bayraktar or something like that, that UAV, they've got Kevlar. So if the UAV or aircraft lands, you've got debris, or you've got lightning strike, or whatever impact you have on the structure, it can absorb that. Because for impact, you need absorption, energy absorption. So that Kevlar, which often put at the outer mold surface, on the outer layers, absorbs that energy, protects the underlying CFRP, and allows that CFRP to act as a high stiffness light material. Okay? Any other questions? So, for ductile material, aluminium, you're familiar, there are some failure criteria. I'm not going to go through them in details. You should remember the term von Mises and Tresca. And I put this slide here for you just as a reminder. I know for a fact level 2 you've done this. So we use von Mises stresses, and we say Tresca stresses or maximum shear stresses. All the values are given here. All the formulation is given here. Let's not go through it. We don't have much time. And also, probably you've heard less about this one. There's another failure criteria. They call it Drucker-Prager. These are the failure criteria that we associate with metallic material. But when it comes to failure surfaces, when it comes to composites, what do? We can't make use of anything. One of the common mistakes I've seen, even unfortunately with academics, my colleagues, and more predominantly with the students, student projects, they do all that thing, simulations with composites, and when they write the report and they give me the contour plus of von Mises stresses, what's that supposed to mean? Nothing. Absolutely nothing. That means nothing. It doesn't apply to composites. Okay, it's just for aluminium and metallic material. So that's where the fun starts here. All of that was introduction so far. Yeah, I'm sorry. Before we go through this, have a 5-10 minute break. I think I can see your face is a bit tired, so I'm going to have a break. I think in the first section of recording I didn't record the screen grab, so probably you just hear me talking. But apologies for that. Okay. So now I think this is a very, very, very important and critical aspect of composites that you need to know. I'm very proud of these slides because this is something that I've been lacking myself when I was a student, even when I was PhD student. Not many people would know, and if they knew, nobody would tell me. That's a shame. but yeah, over the time and experience and all of that, I finally figured it out and tried to put something together. Hopefully you can benefit from it anyways. And I mean it, nobody would tell that's so bad in the world of academia. I mean, there you go. So, we did mention in the previous lecture, we assume composites predominantly behave in a two-dimensional state, not three-dimensional. So, putting that into perspective, there are some failure criteria designed or developed to characterize the performance of composites and to understand when they fail theoretically. At the end of the day, the truth is experimental and experimental observations, and these theoretical models are developed based on some mathematical formulation and experimental observations. Okay. But yeah, they've developed some analytical solutions that would be beneficial to know about them. So for unidirectional composites, and call it, CFRP, GFRP, anything, it could be another sort of material. But generally speaking, we focus on carbon fiber and glass fiber reinforced polymers. As you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I challenge you to go and find any textbook that would give you all the information about that. So I've put these together based on some textbooks and literature and some of my own experiences, and these are generally the failure criterion that are identified for characterizing, for understanding or predicting the failure point of unidirectional composites. That's the key here. The key word is unidirectional composites. And this section is where most academics even don't know it. So they, by mistake, most of them, incorporate these criteria to bidirectional composites or woven composites, unfortunately. But there you go, let's carry on. So what we will do, we'll go through all of these failure criteria, and then we'll focus on bidirectional composites, which are woven. So you've got plies that have fibers in the 0 and 90 degrees at the same time. And we'll have a sort of skim through the three-dimensional stress state and how do we deal with those scenarios, which you will see mostly in defense applications for impact resistance. So, and that 3D stress state is where you have, not only you have fibers going in the 0 and 90, you also have fibers going through the Z direction, just stitching up the whole thing together so that it wouldn't delaminate under the impact, or delaminate less under the impact. So the first one of these criteria is basically maximum stress failure criteria, or maximum stress failure criteria. We'll probably focus on this more than required, but we'll take it from there. In order to understand this failure criterion, you need to know XT is defined as tensile strength in the ply direction. T represents tensile or tension. And X generally in composite represents the direction 1 or direction of the ply. XC represents strength of the ply in compression in direction 1. So this is direction 1, or you could call it X. This is direction 2, or you could call it Y. And respectively, YT and YC represents tensile strength in the tension and tensile strength, compressive strength in the direction 2, basically. Is that clear? And S is the shear strength of the ply. And something I want you to sort of put it somewhere in your mind or memorize it. Generally speaking, shear strength is little to do with the fibers. It's a characteristic of the matrix. So the fibers mostly contribute to this strength, but the shear really is inherited from the matrix itself. That's why you often see that the shear strength of different composites having different fibers but with the same matrix are pretty much the same. So what this failure criterion says that if existing stresses in the X direction is less than the strength it fails. If stresses in the y direction are less than strength in the y direction, it fails. Or if shear stresses in the material as a result of the external loading is less than the shear strength, it fails. Simple as that. I've seen many companies adopt this kind of approach. It's a very simplistic and one of the original or initial failure criteria that has been developed for composites. From this perspective, we often like to know principal stresses in the material, not von Mises. So often is the case that we compare the principal stresses with these values, and if it's less than that, we're fine. If it's greater than that, we're in trouble. If you recall from, I think it was the second slide or third slide this morning, we came up with a prediction for the strength of apply using this volume fraction rule. Oh, they call it rule of mixture as well. So strength of the fiber times this volume fraction, strength of the matrix times this volume fraction will give you roughly the strength of the composite ply. We can ignore or safely ignore that bit, say this is almost zero. Matrix doesn't really do much in load bearing sort of mechanism. So you can approximate that by just this term here, as you can see. Understood? But I did mention that this is just a prediction and an approximation. To give you an example here, this graph is for a glass fiber. And glass fiber has the fracture stress is 3,500 megapascal. 3,500 megapascal. But when you try to adopt this, you would expect to get something, let's say 3,500 volume fraction of 60. How much that becomes? A volume fraction of 50 for glass fiber. We just use a calculator. 3,500, half of that, roughly, we're talking about 1,750. But in practice, it's seen that it oscillates between 1,500 and 2,500 in experimentation. But what you get from that is 1,700 roughly. Okay, so you can see it's an approximation. It falls between the lower bound and upper bounds. But if you wanted to know the exact value, you need to do the test, and that often happens, in the form of when you handle during the manufacture of the laminate, the handling, the chemical attacks, and all of that, even before the whole thing being assembled, could influence this value. So this rule of mixture, if you like, will give you an approximate figure, which is good enough for if you don't know a value and then you want to have some idea, but by no means should you use it for a sort of design activity. I think this slide is quite important as well. So if you look at the volume fraction for e-glass, I've given you, so these numbers is good to have in mind, always have it in mind. Have the rough idea of the figures. Volume fraction for e-glass roughly 60%, high strength carbon 60%, Kevlar 60%, carbon balance class 40%, a woman basically. For a woman, it's roughly 40%. And these ones are quite important, the figures that I forgot, so I'm to blame. Strength and tension, strength and compression in direction Y, tension, compression direction 2, and shear strength. Just compare the values, digest it, maybe spend 10 seconds on it before I better be quiet so that you can focus. So, YT, or strength in the perpendicular direction to loading, I said we generally assume it to be 0. You could assume it to be 0 to be safe. But it's constant. It's always between 20, most of the time, between 20 and 60 megapascal. If you compare it with XT, which is 1,400, it's almost non-existent, negligible. So YT, perpendicular to the, or where you've got the matrix only, it's roughly between 20 and 60. The compression value is, generally speaking, for composites is between 100 and 150. That's again something to bear in mind. And the shear is dependent on the proportion of the fibers. But what I want you to sort of pay attention to is you have E-glass and you've got high strength carbon. They've got the same shear strength. You see? 70-70. It's got nothing to do, to be scientifically correct, it's got little to do with the fiber type. It's purely the matrix. The same matrix is being used, and therefore the same shear strength again. And I'll give you one example of how to, let's get to that. I'll not confuse you further. So, the maximum stress failure criteria. I'll give you another maybe 10 seconds before I start talking. But don't be overwhelmed. We'll go through some tutorial questions that you need to solve. Hopefully that will sort of bind things together. Can anybody explain what's happening on this slide for me, please? What's happening here? Yeah.
Is it how the strength changes as you move through different when you're looking at different directions? So you move from the X and Y, which is purely perpendicular in the direction, as you move through the angle, how those strengths change.
Yeah. So essentially, give or take. So if you look at, you've got apply here. You've got X direction, Y direction. And these are, X and Y are always loading directions. On the other hand, you've got the ply orientation, which we call it LT, or in other terminologies, they call it 1, 2. 1, we always say material direction, 2 is perpendicular to the material direction. In this particular case, this ply is oriented theta degrees, as you see here, with respect to the loading direction. From lecture 1, we should recall that stresses in the L direction, or material direction, or fiber direction, are associated to the stresses in the X direction through this transformation. The same could be said of stresses in the T direction, or direction 2, which is here, and the shear stresses. From the maximum stress failure criteria, we know that sigma L, or stress in the L direction, material direction, should or must be less than the strength and negative of strength in compression. The same could be said of perpendicular direction and for the shear. So essentially we are rewriting this equation here. Let's go back here. Oops. So this equation here, okay? We are rewriting it based on xy, based on xx, or the loading direction. One of the informative things about knowing how the strength of each ply changes with different orientation. So if you orient the ply in 0 degrees, you would expect the strength to be the same as the fiber, or similar to that of the fiber. So what we're trying to achieve here is that, let's say the loading is in tension in this case. Focus on tension. tension. So if your ply is 0 degrees, or maybe here, let's say it's 5 degrees, let's say 3 degrees. So between 0 and 3 degrees, you get the maximum strength for the ply. So where you need the maximum strength for the ply, you know that the orientation is something between 0 and 3. But the moment you deviate from that 3 degrees, let's say your fiber is misaligned for some reasons, manufacturing faults. Instead of attempting to get 0, you get 5 degrees. It's quite informative, this one, because you see the moment you deviate from that fiber from 0, intended 0, let's say to 5, the strength of the ply reduces. And that stress at these points, or strength at these points, are quite significant. It's a drop. It's a rapid logarithmic decline. So you need to be careful in your manufacturing. So in this case, from 0 to 3, you get the maximum strength from the ply, the best out of your composite. From 0 to 10, and you can see what happened from 10 to 20. The decline is quite significant. And then when you come to that point, what degree is that? 30 degrees. So when you hit around 30 degrees, S over sine of theta, cos of theta, what's that associated to that? The shear. So essentially your ply, instead of acting as a load bearing through the fiber, it becomes a shear ply. And strength changes as well. And as you go along, let's say you get to 90 degrees, the strength goes around between 20 to 40. Let's say 35 at that point. So you can see, as the orientation, that theta up there, when you're 0, you get the best in terms of load bearing. The orientation changes, let's say to 30. It goes more towards shearing. Yeah, what's the question?
So if you carry on rotating it, I don't want to say all the lines would end up looking like a sinusoidal wave, but is this kind of like stress transformation where you
What do you mean by sinusoidal?
like you'll carry on if you carry on rotating it, or you carry on, you make a graph, you carry the lines on.
You mean that
Kind of
theta
like-
from 90 goes to 100?
Yeah, like 360, like carry on. Because
So-
I'm kind of like a 2D shape, like a
No,
2D
uh,
but just more stuff.
So what happens if, let's say you had this, let's say this is 5 degrees. 5 degrees, okay?
Yeah.
For the sake of argument. Then you say, what if this happens? And that's 5 degrees as well.
Yeah.
They're pretty much the same.
Yeah,
So there's one way of demonstrating, we'll get to that actually. You've got an exercise on that, by the way. One way of that is showing it from 0 to 90. The other way is to show the whole 360. So you can see.
With it carrying kind of oscillating between
I didn't want to go there but I can quickly show it to you so that you have something in your mind. I don't like any questions remaining. You see that kind of graph? So, for example, for 0 degrees, it's got the maximum, and then as you degree go to 20, 40, 50 degrees, what happens? It's quite symmetric.
Yeah.
So I would be asking you to construct that sort of graph as well. Anyway.
Thank you.
That's all right. So another one is, so that's the maximum stress, which is massively used. I mean, quite common failure criteria that many people use it. Maximum strain is another one. So instead of dealing with stresses, they say, let's see the maximum strain. Compare the strains with the failure strain. Okay. If strain in the x direction is less than the failure strain, it fails. Very simple. Strain in the y direction is less than the failure strain in the y direction, we are okay. The same could be about the shear strain. Simple as that. I mean, there's nothing. These two criteria are very easy, but very quite used significantly for initials, because they're very primitive, rudimentary, but very simple to use. So for preliminary design cycle, it's good to use them. The formulation for that similar to the previous, instead of using sigma L, we are using epsilon L, or strain in the L direction, material direction. Just to remind you, this is L direction. Epsilon T, strain in the transverse direction, the shear strain. And all of these, modulus of elasticity in one direction, modulus of elasticity in two or T direction, shear modulus in the plane, and they are all associated to the stress in the loading, sigma xx and sigma xx. So from this perspective, essentially, because you're using strains, finally your stresses would look like should be bounded within these upper and lower bounds. So as long as you're bounded within these upper and lower bounds, you're fine. The moment you exceed these bounds, essentially means your composite is failing. Maybe it's a good practice just for the sake of clarification. I'll just copy paste the one you had in the. Let's copy that just to have it next to what we had here. Oops. Just put it there. Put it there for now. Just as a comparison, just compare it. See how it's changed. So that's maximum stress criteria. This is maximum strain criteria. And just spot the differences. You can see the shear component hasn't changed. It's the same. But the in the one direction sigma xx, it's got Poisson's effective ratio in there, nu LC cos of theta to the power of 2. So it's got these components as extra for the maximum strain failure criteria. These components are extra. This is pretty much the same as that one anyway. Slightly different. It's just because you're comparing strains instead of stresses. We've used this one for Piaggio, Italian aircraft manufacturer. So that's the way they do it. But different manufacturers do it differently. Now things become a bit more intense. Another one is, maybe this is one of the first attempts to characterize the failure of composites. It's called Tsai-Hill. There were two scientists, I think they were Japanese, Mr. Tsai and Mr. Hill. So they combined efforts and came up with a failure criterion, purely experimental. So it purely comes from the experimental observations. It's used extensively. Even in the finite element software, Abacus, it's got Tsai-Hill formulated into it. So it's one of the widely used failure criteria. So the way, it's very simple. It's very good for initial design procedure or stages. Based on the experiments, something to bear in mind. The way it deals with it assumes, it doesn't see fiber matrix. It doesn't see any of that. It just assumes it's an orthotropic material. I don't care it's fiber or it's matrix. It's got a modulus of elasticity in that direction, let's call it EX, and it's got a modulus of elasticity in that direction called EY, and that's it. So it's essentially smearing the stiffness of the ply in the form of an orthotropic ply with EX and EY. Doesn't care about any of that anymore. It just sees orthotropic, it's got X direction, EY direction, that's it. So from that perspective, it doesn't distinguish between matrix failure or fiber failure, or it just doesn't see fiber and matrix. That's the way it deals with it. That's essentially that. If applied stress in the x direction to the power of 2 over strength of material to the power of 2, it's a quadratic equation. Take away that, add that equals to 1. If it becomes 1 or above 1, composite fails. If it's below 1, you're fine. As you can see, there is no distinguishing between whether the loading is in tension or in compression. There is no distinguishing between the fact that is it a fiber fracture, is it a matrix fracture, is it delamination? Because at the beginning of the lecture, we saw all that failure criteria: delamination, debonding, matrix fracture, longitudinal transfers of matrix, all of that, those 5 criteria. You remember that? It doesn't see any of that. Very simple. Whatever they look, just stick it in, see what happens. That's why it's not detailed enough, but it's good enough. I mean, for most initial phase of your design optimization or conceptual design, it's good enough. I mean, it works, but not for detailed sort of procedures. I know for Airbus, we don't use that. We use Yamada-Sun, was it? No, I can't remember but we don't use this. NASA has developed its own sort of failure criteria. We'll see that. It's called L0R. We'll see that. But yeah, for detailed, complex structures, we don't generally use it. Another one was Hoffman. That's quite a famous one. They use it to some extent. Altia Hyperworks uses Hoffman. Abacus purely uses Tsai-Wu. I don't know about ANSYS, so you might need to check it. What ANSYS uses. I'm not an ANSYS guy. But Hoffman is being formulated into Altia Hyperworks, Hypermesh, and OptiStruct. So the way that criteria works is, it's all given to you. Because Tsai-Wu was purely experimental, Hoffman decided to improve on it, to add some mathematical logic behind it. So this is not an experimental, it's a mix of experimental and analytical, mathematical. So that it was the first attempt to mathematically formulate things as opposed to experimental observations. So Hoffman decided, probably German, decided to do so. So he came up with this failure criteria. And on top, I put Tsai-Wu. So what I would like you to do, just compare them together and spot the differences, please. So, what's happened to you guys? Do you see any improvements here? Hmm?
Considering both strengths and tension.
So it distinguishes whether the loading is intentional compression, which is a massive improvement itself. Anything else?
Longitudinal, transverse and longitudinal.
So that essentially is stress in the fiber direction divided by strength. So these are stresses in the fiber direction, whereas that one was in the loading direction. Okay, that's different. But you can see it's a bit more comprehensive than the Tsai-Wu. So we're getting there. So as time goes by, these formulations become more advanced. Until we get to the NASA one, you'll see I never use it because I need to. If you want to use these kind of failure criteria, you need to use Python programming to incorporate it into finite element software. It's not in the finite element software. So companies have sort of used Python programming to formulate that into as a subroutine. It's not, unfortunately, it's not. That's one of the annoying things, is that it's not formulated in the software. That's very annoying. But there you go. Another one is Tsai-Wu. So Mr. Tsai has been quite active. So he came up with Tsai-Wu with Mr. He and then now Mr. Wu in a collaboration. Have a look and see how different it is with the Tsai-Wu then, please. As you can see, the Tsai-Wu is pretty much the same as Hoffman. It's not that much different. It does distinguish between tension and compression, which is a good thing. But the shortcoming with these failure criteria, none of them talks about matrix cracking, does it? None of them says the matrix cracking is taking place. So this shortcoming is, I think that's a quite crucial one as well. So the Tsai-Wu provides unrealistic values for biaxial loading. So if you've got one in the x direction and one in the y direction loading, it will give you, so you need to know about the limitation of each method. So the Tsai-Wu is not going to give you good failure criteria or good predictions in that sense, but for other type of loading, it will either give you acceptable or excellent failure criteria. It's been sort of evidence in the experimental testing and validation procedures. Something, so if you've got a biaxial loading, maybe it's not the best failure criteria to use. Something to bear in mind. That's the one, LARCO3 failure criterion, which was developed by NASA. It's quite intense. I'll put it up for you.
Does anyone other than NASA use this?
Yeah, lots of academics use it, but you have to formulate it. I mean, generally, you need to have a PhD or a postdoctoral student to create that Python programming for you and then incorporate it. I don't have time for it, but if you're interested, you can do that. If you want, it's up to you guys. So have a look at that one, see what you see. Matrix cracking is incorporated, which is a massive improvement. None of the failure criteria outlined so far dealt with matrix cracking. So that is also included. And also includes whether the matrix cracks in tension or compression, which is quite significant. I wouldn't be surprised with the financial backing that NASA's got and all the scientists they've got, they can develop some stuff like that. Fiber failure is included. That's all we need really. But there are some parameters, or they call it, you can see properties such as G. These parameters are all given out. There's no need to go through it, but it's very intense. One of the problems with this is that there are a lot of parameters that you need to know, and that requires experimental testing. So for practical, for a big company like NASA, it's feasible with that budget and testing and all of that, because you need to know about the fracture toughness of materials. So G1C, G2C up there. So that G, small g, is essentially the ratio of fracture toughness in mode 1, fracture toughness in mode 2, divide them, it will give you G. And finding G1C and G2C is quite a significant effort itself. I mean, the testing for that is quite tricky and significant. And then you've got eta, and all of these formulations, you need to know all of that. And that requires a lot of testing, but it will give you a good prediction and approximation. So the failure criteria that we've discussed so far, there is something that is lacking in all of them. Which one is it? Do you know that? One of the failure criteria has never been discussed or mentioned.
Failure mode.
Yeah, what failure mode? What this one's saying about whether it's matrix cracking or fiber fracture. Delamination. None of these failure criteria is about delamination. And it's a tricky one. So for delamination, we just use finite element software. They call it cohesive zone modeling. So we model delamination, the delaminated layer or potentially delaminated layer, and see if it delaminates or not. So none of the failure criteria that I will discuss, will talk, says anything about or mentions delamination. They're not capable of doing that. Even this NASA developed one. Another one is Hashin-Rotem. The Hashin-Rotem one is. Well, have a look. First of all, have a look before I make any comments. So what do you see here? It's a very simplistic way of dealing with composites. It does include fiber failure, which is a good thing, and it also considers matrix failure. which yet again is a good thing. It distinguishes whether the matrix failure is in tension or in compression. I mean, very simple. If I wanted to use it, maybe probably you would use this one because it's not too much. You don't need extra parameters to formulate. Okay, and we've got some examples. So let's stop here for now. So we've discussed it up to this point, Scott. Any questions before we carry on? Because we've got 2 tutorials outstanding from previous lecture.
So what is the, why do you not use that last one then in comparison to the last one? Because they both consider matrix.
Why didn't we use?
The last one, because it was a lot simpler, but it still included those 2 failing modes. So what's the big drawback of that?
Well, this one, Hashin-Rotem. Let me just. Yeah. Okay. So this one is often good for matrix cracking. Okay, matrix cracking, and this is the bulk of what this failure criteria is suggesting. It is not good for fiber failure, and that's often the case. They combine this with another failure criteria. So, yeah, I'll get to you. So they use Hashin-Rotem combined with Tsai-Wu to obtain the failure criteria of the laminate. Because Tsai-Wu is good for fiber fracture. It doesn't say anything about matrix cracking. This is telling about matrix cracking. So if you combine them together, that often happens that you combine for Tsai-Wu to use Tsai-Wu for fiber fracture and this one for matrix fracture. Okay? And this is mostly predominant where you have shearing of your material. So if you've got axial loading with tensile and compressive axial loading, it's not that precise. So hence, it's always been used in combination with another failure criteria that can see, which is good for tensile and compressive and all that direct loading, and can give you a good fiber failure sort of.
Sorry to answer it. With the mixing matrix.
Oh yeah, I answered that.
Yeah, sorry, with the matrix.
Yeah. So yeah, that's why it's just being used with. And by the way, I've always. Can you see it? Yeah. I create some notes for each slide. Not all of them. The slides that I think are quite important, and these are quite extensive explanations. So if you need to understand more about them, just go through the notes as well. That will give you extra information that you would require. Okay. Any questions? Okay. In that case, let's close this one for now and go back to the previous lecture. Laminate theory. I'm not going to be talking until we are certain that you're able to solve this problem. Problem number 1 that we started. Okay. Can you please fire up your Excel or computer, whatever you have, try to tackle this problem, and I want to have a number associated to your solution. So yeah, working groups, solve this example. You've got some ideas now, and we'll take it from there.
So add up all the thicknesses and then divide by. And then, so you do, so for your set A, you do half of your 20 apply thickness of like apply to that, whichever one the model.
This is 0 degrees.
And then you do minus your
We're going off the assumption
and then I is minus. No, this is half. These values here.
Yeah, from the top. Yeah.
So very much best idea to change it. The reason I did 2 minus 2K is because for Z E plus and then so then if you do all that, then you times by negative 1 depending on which way you take it. I took 1, 2, 3, 4, 5, 6.
Just change the left one. That is a number. Change the left ones. Don't be touch right. So like that. Yeah. And you can change the right one. Yeah. When you look to oh my god, maybe you can find that. Did you see how there's a 0? Manufacturing not scale. And then I'm not doing it. I'm not doing it because unless you know
Isn't that solid work?
For 1655
People are in because our fighting the guy doesn't. Yeah, he didn't feed much.
No. Your Q165, yes.
yeah. 166. Oh,
You missed that one. I mean, that's a whole different issue about.
So I've put the validation here. So your ABD matrix should look like this. So I think, guys, can I have your attention? I know you're working on that thing, but I came across this industrial example that we've been doing with Piaggio. I thought that will put things into perspective, how we do it in industry, okay? So Piaggio is an Italian company, aircraft manufacturer company. So if you look at these, so they've done a lot of in-house testing. Testing. By which, let's have a look at this. So, for example, we've done coastal isotropic layout test in the tension. We call it open hole tension and all of that. And we find the allowable strains. Can you see the strains? Allowable strains. Different allowable strains at cold temperatures. So at different temperatures, cold, room temperature, elevated temperatures. As you can see, at different allowable strains for different temperatures. So a lot of testing and a lot of coupons. We also have done a sort of testing with, we call it soft laminates. They're not too stiff. You can see angle ploys are soft because the stiffness is not too much. The same can be done in, we call it cold temperature, cold dry temperature. D means dry, cold temperature dry, room temperature dry, elevated temperature wet. So high temperatures and wetness are bad for aircraft, for any structure. So this is the worst case scenario. High temperatures and wet conditions. room temperature is like this. So at this room temperature and ambient moisture, we just measure the composite as well. And also, cold temperature makes the composite brittle. And if you look at the bugger. So if you look at the strain values, all of these would be calculated on different. So we've done it on hard laminates as well, very tough laminates. I mean, it's all 0.90. You can see it. Yeah. Quasi-isotropic layer. So we do. So essentially, what we're doing by the means of testing. There is no theory here, it's all experimental. By the means of testing, and a lot of it, we find the allowable strain of the laminates. And then, in this particular case, we go and simulate an FEA, we simulate a particular part of the aircraft. Okay, all of this is composite. So apply aerodynamic loading, and we'll come up with all the loading. We just mask the holes, the fasteners, because fasteners are fake, provide fake stress elevation in the contact cloth, so we mask them. So there's no fastener here, we just take away the elements associated with that. Essentially what you would get, stress distribution in the components. This is everything you see in composite. If you look at the contours, for example, what does it say? Composite strain, minor strains. Minor means it's in compression, so value should be negative. So, and then we compare it against the allowable strain. So we get the maximum, in this case, maximum strain, and we compare it against the allowable strains that we obtain here. So if the strains are less than that, we're fine. If it's not less than that, it means you're in trouble. We need to add the number of plies to limit the strains within that range. Okay? I thought maybe that's a good example of that's as real as it gets. Finite element, find the strains, compare it against allowable, and then decide whether the composite fails or not. Okay? And that's often the most practical way of dealing with composites in industry. Test it, find allowables, and generally the strains, not stresses. That's what happens in industry. So we compare the strains with respect to the strains as a result of the loading. Okay? I thought maybe that's beneficial for you to just to have an example. But yet again, if you look at these sheets, that's for 80 degrees Celsius. We do the same for minus 55 degrees Celsius. Find the stresses in that temperature. If I look at the this one, for example, I don't know what, you get different values of a strain, and then you compare it against so minus 55 is cold dry temperatures, and then we compare it against allowable. Is it good? Is it not good? And we'll decide on that. I thought maybe that's sort of beneficial to know. Don't say. Okay, the final thing I would like to add for this session. Obviously, we didn't have time to go through this thermal expansion and moisture. Probably in the next sections I'll cover that again. That's fine.
Do you remember the thing we said about there was the error with the epsilon being 3 to the 2? We told you at the beginning of
Oh, okay. Yes, you mentioned that, didn't you? I haven't looked at it yet, but if there is any mistake, the same as that epsilon xy, yeah, that's fine. That would be my bad.
Yeah, on the left side there, it's the beta.
It should be beta 2. I'll fix it, don't worry. Thanks for pointing that out. The other thing I wanted, maybe the significance of this exercise, this exercise is that often the case, you need to find out the homogenized, they call it homogenized modulus of elasticity. Trying to create an analogy with metallics. So because in a laminate with different stacking sequences, you've got different plies, each having their own modulus of elasticity. The idea is to find out what is the total combined modulus of elasticity of the laminate, not the ply, the whole laminate. So therefore, there are some formulation that you can exploit. For instance, here, let me just put it into the presentation mode so that I can annotate it. So if you look at this one here, so where you've got your A D matrix, the inverse of that will give you alpha, beta, whatever, delta matrix. So that's essentially this is the inverse of the above matrix, ABD matrix. Okay, you can readily obtain that via Excel, and you can see in that tool how it's done. The modulus of elasticity is defined as 1 over the thickness of the laminate, T, that's the thickness of the entire laminate, and alpha 11 is this component of alpha, beta, delta matrix, okay?
Why are we, because we're working out EX, I'm assuming, is this for like that question before, where it gives us EX, or is this for a different
No, you need to calculate EX.
Even though we're given it at the beginning.
Well, that E is associated to one ply only.
Oh.
And in the direction of the ply. So your ply could be oriented at 45 degree. The other ply could be oriented at 0 degree. The other ply 30 degree. So what is the EX of the whole laminate?
Oh.
The entire laminate. So so essentially we are trying to smear the stiffness of the plies and see that laminate as an orthotropic material, as a plate, like an aluminium plate.
Oh, so you kind of just turn it into one thing.
Yeah, so I want to find out, to just make the calculation easy, to find out what's the EX and what's the EY or modulus. So this laminate, in a very simplistic way, is under tensile loading. And this laminate could have 20 plies, 30 plies, 40 plies, you name it. In the case of an aircraft, it could be 100 plies or 300 plies. I want to know this laminate, which has got so many plies, what's its EX and what is its EY. So I don't have to deal with all those number of plies and just see it as one plate. Simple as that. So the formulation is so alpha 11, as you see, which is that component. EY comes from alpha 22, which is this component. And the shear modulus of that plate comes from alpha 66, which is this component. But here's a delicate point for composites. This EX and EY and GXY that we obtained is associated when your loading is membrane, which means inside the plane of composite. In this particular case, you've got a tensile, it could be compressive, or you can have another load perpendicular to that. But it is also well possible that your composite could undergo bending. So bending is not in the plane of the composite anymore. You cannot utilize these EXs and EYs for that kind of loading. So for those, you need to make use of EX and EY, which is for bending. It's got a different category. This is something that many people, yet again, they've got misconception over it and make mistake. So it's really down to your loading. If your loading is membrane, inside the plane, NX, NY, inside the plane, you use that EX and Y from the previous slide. If you have the bending, the EX associated to that, or the modulus of elasticity for that type of loading, you can see you've got cube of T instead of the T. And instead of using alpha matrix here, we're using, so not that one, we're using the delta matrix. So that's something, it's a very delicate note that you need to bear in mind. It's purely dependent on your loading. Yet again, I know I said it, but I will repeat again. You need to look at your loading. If your loading is, for instance, if you had a composite beam like this, in a three-dimensional format, let's say, that's a composite beam, simply supported, and you've got a point load there, right? This structure is not experiencing much of membrane loading, it's all in bending. So you should use EX and EY from here, from this calculation. But if you've got a structure, which I explained, is a plate. It's a simple plate, and you pull it apart. So the loading is in the plane of your structure. It's not bending, so you need to make use of EX and Y previous slide. That's something to bear in mind for further calculations, or if such a scenario crops up. Okay, I think we've pretty much covered everything. Probably at the end of the next lecture, I would briefly touch upon the thermal coefficients and all of that. It's a very brief 2 slides really, not much. But the tutorial for that is quite important. You could definitely make use of it for your coursework. And you will need to go through it. But I think that's enough for today. Any questions before we wrap up and say goodbye? Yes, go ahead, please.
What do the little apostrophes mean?
Where?
In the arrays on the C's and Q's.
What slide number?
Like when you have the little apostrophes over the sigmas, or on the bottom here. They show up quite a lot, but I don't know what they actually.
What slide is it from? I can't remember.
That's on the Hoffman one, but there were ones.
Just bring it up.
Yeah, in the temperature and moisture effects as well. In the Q matrix and in the.
Let me just stop recording for now.